Hi, hello. So I want to do a couple of homework problems for Chapter 6, Section 4. I'm going to do a confidence interval and I'm going to do a hypothesis test. So the main difference between what we're doing now and what we've done in the section before that, section before that, is that we're in a different context. So we're just simply thinking about what it is that we need to adjust in this context. The constants are what the hypothesis test means, what the confidence interval means. Every one of these has some small twist, but once a person gets used to the big idea, then the twist is just a matter of saying, oh, in this case, for example, in this case, we have to use a t-curve. So I want to do an example that shows the twist, while emphasizing that it's not the case that every chapter is a completely new ball game. That's just not right. Instead, it's going to be every section. Instead, every section has the same ideas. Confidence interval means the same thing, and hypothesis test means the same thing. It's just a question of adapting to some new context. And then I'm also reminding you that all the formulas for all the things in Chapter 6 are all together on one page. It's a good idea to write other things on that page. If you say, I got to remember, write t-curve next to this section, for example, or whatever other things you find useful, and put it all on one page. And then when you're doing the problems, you're not hunting around for that was here somewhere, So that's helpful. Okay, so I want to do a confidence interval and hypothesis test, and here are the formulas that we saw. So we are in a context where we are thinking about the difference between two means. We might have an average for men and an average for women. We might have an average for treatment group and an average for control group. We might have an average for people, average blood pressure for people 20 years ago, or average blood pressure for people today. We have two different averages. We want to know, we want to understand the difference between those two averages. We are in a context, however, most typically in a context, where not only don't we know the mu1 and mu2 and have to get by with x1 bar and x2 bar, that is the sample average and the sample average. Not only do we not know the population averages, that's what we want to know, not only do we not know the population averages and have to get by with the sample averages, but also we are in a context where we don't know the standard deviations either and have to get by with the sample standard deviations. Now, in proportions, it so happens that the proportion can be the standard deviation for proportion can be calculated. The standard error for proportion can be calculated from the proportion p times 1 minus p over n, take the square root. So you can calculate the standard error for the proportions in that context. So this complication doesn't arise in proportion, but it does arise in averages. That we're in a context where we not only don't know the population averages, but we don't know the population standard deviations, and so you have to look things up on a t-curve. In a context where there are two averages, then you have to look it up. You remember the degrees of freedom. You take the number in your sample minus 1 and the number in your other sample minus 1. Take the smaller of those two numbers. That's called the degree of freedom. You have to enter that in order to get the right curve. Okay, so I want to try here two examples, and the first example that I had in mind was 6.190. So I'm on page 458, 6.190. Let me see if I can bring up there we go, bring up my thing, and not easy to read, but it says 99% confidence interval for mu1 minus mu2. Do you see the mu1 minus mu2? So they're telling me that they want me to figure out where is mu1 minus mu2, and they want me to be 99% confident about it. And then, of course, they use some numbers, x1 bar, s1, and n1, x2 bar, s2, and n2. So I'm going to do the calculation. In particular, I'm going to do the part that's different from anything we've done before, from other sections, from the proportion sections. I'm going to use the t-curve. Okay, and obviously you should look this up on your book rather than try to read it from my ridiculous screen. Okay, let's try it. So 6.190. And the information that I'm copying down is they want a 99% confidence interval. And they also gave me that x1 bar is 501. S1 is 115. and N1 is 400. I think I copied those down wrong. Boy, it'd be bad if I started out with the wrong numbers. I got it right. Okay, and then X2 bar is 469, S2 and N2. 469 and S2 is 96 and N2 is 200. Okay, so we chose this because the numbers are all different. Sometimes N1 and N2 are the same. That happens a lot in practice. But I chose different numbers just so that a person won't say to themselves, you know, which of the two number 30s is that one? Okay, and of course I'm simply doing the confidence interval formula. So exactly the same stuff as confidence interval always is. I'm looking here at x1 bar minus x2 bar. Plus and minus, because confidence interval is always plus and minus. Now this is means, so I'm not saying Z star, I'm saying T, like tango, star. And then you have to have the darn formula, but of course we have that written out in the book, so it's not the end of the world. It's S1 squared over N1 plus S2 squared over N2. And then once I get the T star, I fill in the numbers, and in some sense I'm done. The rest is a calculator job. Anybody can flub it up, but that's just a flub. That's not conceptual. So let's do the T star just because that's the main idea. Okay, so I'm bringing up stat key. If I can work all these. There we go. Bringing up stat key. I'm going to the T curve. Oh, come on. I lost stat key. There it is. Going to the T curve. And now I'm asked to write in the degrees of freedom. So you remember that N1 is 400 and N2 is 200. Pick the smaller of those two numbers. I mean, of course, it's 200. Pick the smaller of those two numbers and then subtract 1. And again, I understand that a person can say to me, the -1 stuff is a little on the weird side. Very true. I talked about it in the beginning of class, seems so long ago when we were still together. It has to do with, in a data set, how many things can actually vary. But for our purposes, for getting the answer, just put in 200 minus 1. So 199. All right, so there's a perfectly sound reason for it, but we're trying, you know, with folks away here and all, I'm just simply trying to help folks get the answer. Okay, and I think I was looking for a 99% confidence interval, if I remember right. So I'm going to pop up the two tails and ask, what does it take for the middle to be not 95 but 99? So here the mistake to make is to type in a 99, type in a 0.99. Okay. I've been there. And what I'm looking at down there is 2.601. Okay, 2.601. So that's the number that I'm going to enter in, 2.601. 2.601. And again, I'm going to go through and do all the work, but in some sense we're done here because the rest is a calculator job, and of course everybody can use a calculator. So that's 115 squared over 400 and 96 squared over 200. Plus and minus at the beginning, and 501 minus 469. I know you can do that in your head, but I like to have it all written down in one place. Okay, I'll break out my calculator. Here we go. But I know everybody can do it. Let's see if I can do it. So 115 squared over 400. 115 squared over 400. And my calculator seems to think that's 33.0625. It doesn't have all that many decimal places. I'll write them all down. 33.0625. And then 96 squared divided by 200. 46.08. $2.601. And this must be, let's see, 501 minus, it'll be 31, 32. Okay. Okay, let's see how I do. I like to see. I like to not do this all in one go, but to break it into a couple steps because then I'm less likely to flub it up. Let's see how I do. 33.0625 plus 46.08. Take the square root. And I got to what, 8.89. I'm going to round it to two decimal places, so I'm looking at 8.90. 8.90. I'll write it in. 8.90, 2.601, 32, and a plus and minus. 2.601, I'm sorry about my handwriting. Punch it out. 2.601 times 8.90 equals 23.14. That's actually 23.15 when you round. 23.15, 32 plus and minus. I like to do both ends just because, again, sometimes for some folks in the room, the numbers seem more concrete than the plus and minus, which I'm one of those folks. So 32 plus 23.15 is what, 55? 55.15. And then the other end of the interval is 32 minus 23.15. 8.85. Okay? So again, that's a 99% confidence interval. What does it tell us? It doesn't tell us anything about x1 bar and x2 bar, does not. Doesn't tell us anything about the samples, doesn't. Tells us about the census numbers. Where is mu1 minus mu2? We think, we're 99% sure, that if we did a census of the entire population and found mu1 and found mu2 and subtracted, that the resulting number would be in that range. That's the point of a confidence interval. Confidence intervals are about the census numbers, not about the sample numbers. You use the sample number to calculate them because that's all you got. Instead, they're about the census number. Okay, very good. Okay, then next I want to try hypothesis test. So I had in mind, oops, I lost my paper, number 210 here. Hypothesis test, so I'm going to turn the page and get to 210. Again, emphasizing here that that hypothesis test and confidence intervals mean the same thing from section to section. So each section is not a brand new ball game. Instead, the sections are the old ball game repeated. Different little twists from problem to problem, but something like the old ball game. My goodness, too much light. Excuse me. Sun came out. Okay, so it says test H0, mu1 equals mu2 versus HA, mu1 is unequal to mu2 using sample results, and I'll copy all these down to the piece of paper so a person can read it. So this is just simply a question, not a word problem, just simply a question where you plug in the numbers. So that's exactly what I'm covering today, is in this context that we are working in, the context of two means, difference of two means. How do you do the calculations? The ideas are the same. How do you do the calculations? Okay, so let's try it here. Number 210. And H0 is mu1 equals mu2. Which, as you know, I like to write as mu1 minus mu2 equals 0. And then HA is mu1, they happen to say unequal. Mu1 unequal to mu2. So that's mu1 minus mu2 is unequal to 0. Okay. Okay, and then it gave me some data, and I'll copy it down where a person can read it. So x1 bar is 15.3. x1 bar is 15.3. There's going to be an S1 and there's going to be an N1. S1 is 11.6 and N1 is 100. And likewise, there's going to be X2 bar, S2, and N2. They have to tell you that. You can't guess. They have to tell you somehow. So I've got 18.4, 14.3, and 80. again, I like it. Sometimes these numbers are the same. The 100 and the 80 might be both 100s, for example. But I like to pick an example where they are not the same so that a person isn't left wondering which of the two is the one I have. Okay? Okay, now again, emphasizing similarity problem to problem. So what happens is we always start a hypothesis test with the same two words. Assume H naught. Okay? We hope to show H naught that their position is not really tenable. That is, they are saying something which in the context of our experiment is actually very unlikely. Okay, then the sampling distribution is this. And it always looks the same because I'm not a very good drawer. This is the distribution of x1 bars minus x2 bars. And where is it centered? Why, it's centered at what H naught thinks it should be centered at. What's the spreadedness? It's this formula. The formula is moderately big, but come on. I mean, you know, it's just a formula. You take your calculator. It's not so bad. So the square root of S1 squared over N1, S2 squared over N2. So that's the square root of 11.6 squared over 100 plus 14.3 squared over 80. And again, I like to do it in two steps, in part because I'm not a whiz with a calculator, but also in part because it's easier to go back and check your work. Let's see how I do. Lift up a little bit here. So 11.6 squared equals, divided by 100 equals. So that's 1.3456. 14.3 squared equals, divided by 80 equals 2.556. I won't write them all down. The fifth or sixth decimal place is not going to matter to us. Okay, add them and take the square root. 1.3456 plus 2.556 equals, take the square root equals, and I got 1.975, so I'll round that to 1.98. That's the spreadedness of the sampling distribution, and we know the center. All we got to do is, where is our number, 15.3, 18.4, take the difference of the two, where is our sample lie? So we got to find the p-value. So I got to figure out where is our sample lie. What is our sample? It's 15.3, take away 18.4. 15.3, take away 18.4, and I got a negative 3.1. But don't forget, this is, they told me to do mu1 unequal to mu2. So I got to do not only the negative 3.1 and on down, but I also have to do the positive 3.1 and on up. And I want a total. Okay. So in order to get that, of course, I have to figure out how many standard units is 3.1. Look it up on StatKey. That's the answer. So how many standard units is 3.1? I'm going to be on a T curve, so this is T. It's not the crime of the century if you don't write the letter, but I'm writing it to try to be clearer. And I'm looking at 3.1, take away 0. How far is 3.1 from the middle? Divided by 1.98. Divide by the spreadedness. So let's see, 3.1 divided by 1.98. 3.1 divided by 1.98. And I got to 1.56, or 1.57. So that's the number of T units, 1.57. I'm going to ask StatKey what's the shaded area, and then I got to remember to double it, but that'll be the p-value. So I'll write that in advance here. P-value is 2 times, and I'll figure out, I'll ask StatKey what corresponds to 1.57. Okay, so StatKey, come on, come to Papa. Ah, there we go, very good. Okay, so I got to remember for the right degrees of freedom. Remember here, this is still set up from the last time I did it. So I could edit the parameters, or I could go back to the beginning, and I'm going to go back to the beginning just to remind a person where you find this. I'm on the T curve, so T it is. And now for degrees of freedom, I look at 100, I look at 80, take the smaller of those two, it's 80, subtract 1, so 79. That will give me the right answers. And now I could do left tail with negative 3.1. I could do right tail with positive 3.1. I don't know. I'm just going to do that one just of the two. Excuse me, a 1.57. Of the two, I'm just going to do that one. So 1.57. 1.57 is the standard score. That's the T value that I want, 1.57. And it seems to correspond to a shaded area of 0.06. Don't forget to double it, but we're done. 0.06. Enter it into the piece of paper here. 0.06. That's, of course, 0.12. And that's certainly bigger than alpha equals 0.5. It's even bigger than alpha equals 1.0. We're going to fail to reject. Okay? So again, emphasizing the unity rather than the differences. The differences are important, and I talked about the differences, but emphasizing the unity. We have a hypothesis test. They always go the same way. There are 3 variants. You can have a less than, a greater than, or an unequal. You always assume H naught. Always. That gives you a sampling distribution. It's got a center. The center came from here. And it's got a spreadedness. Those formulas, I mean, they're all on that one page. Just bookmark that page. Then you got to figure out, where does our particular number lie? Our particular number, when we standardized it, lies at 1.57. I asked StatKey, what's the shaded area that corresponds to 1.57? And StatKey told me. Every problem's got a little twist. You have to remember the degrees of freedom here. But they're much more alike than they are different. Okay, very good. So because that was bigger than the alpha value, we failed to reject. Okay, very good. Very good. I hope everybody is well, and we'll see you for the next round.